Assalamu alaikum everyone and a very good morning. This is Suad Zahra Alvi and today I am here to give brief review on my FIP project that is design of ultra flexible skin-like sensor fusion for human wearable monitoring of osteoarthritis. I, along with my group member Abdul Jalil Ahmed, work under the supervision of Dr. Afaq Manzoor Sumro and Dr. Muhammad Waqas. Today's agenda of our presentation is introduction, literature survey, aims and objectives, methodology, results and discussions, which includes application of health monitoring, conclusion, and further recommendation. And last but not least, references. Starting with the introduction of our project, as the world's population continues to age, the more and more people are facing challenges related to mobility and health. According to the World Health Organization, the percentage of population over the age of 65 is expected to double by 2050. As we age, our body undergo a variety of change that can make it harder to move around and stay active. Regular exercise and physical activities can help to counteract these effects, but unfortunately, many older adults are unable to engage in regular exercise due to mobility issues and other health problems. This loss of mobility can have a significant impact on the individual's quality of life as well as their overall health. As the population ages and demand for healthcare services increases, there is also a growing concern about the cost of healthcare. However, by, however, by identifying chronic diseases such as arthritis early on, healthcare professionals can provide timely intervention and treatment to help manage these conditions and prevent further complications. Early diagnosis and detection can also help to reduce healthcare costs associated with these chronic diseases by preventing hospitalization and other expensive medical interventions. One way to improve the early diagnosis and detection of the mobility issue related to the aging is through the use of innovative technology, such as ultra-flexible sensor fusion sensor fusion. By placing these sensors on the body joints, healthcare professionals can monitor movement and detect changes in the mobility in real time. This technology can be particularly used for older adults who may be at the risk of mobility issues such as osteoarthritis and joint degeneration. By detecting these issues early on, healthcare professionals can provide interventions such as physical therapy or joint replacement surgery to prevent further deorientation and improve the mobility. Furthermore, the use of ultra-flexible sensor can provide non-invasive and easy-to-use methods of monitoring joint health, allowing older adults to maintain an active lifestyle with also receiving the necessary care and support to manage any mobility issue that may arise. Overall, the use of innovative technologies such as ultra-flexible sensor fusion can play a critical role in improving early diagnosis and detection of the mobility. By doing so, we can help older adults to maintain their independence and quality of life for as long as possible. Also, we can implement or we can embed AI trained model in our sensor for the detection of healthy and unhealthy joint. And also to make it user friendly, we can design the mobile application. Here is the application of strain sensor. The major application of strain sensor is revolved around monitoring of joints, robotic application, detecting neuromotor disease. This can be achieved by placing the sensor on joints to quantify the results. Wireless network, we can develop the wireless network for the communication or to transfer the data to the AI model, which gave us the result or which will tell us about the healthy and unhealthy joint. Now, the disease we are going to target is the osteoarthritis. Our sensor will help us to detect the osteoarthritis. Osteoarthritis is the most common form of the arthritis. Osteoarthritis is a degenerative joint disorder or wear-tear arthritis. it occurs most frequently in hand, hips, and knees. In the hand, osteoarthritis can cause swelling, pain, stiffness in the joint. As the cartilage wears down, bone can rub against bone, causing even more pain and inflammation. In the hip and knee, osteoarthritis can cause pain and stiffness in the joint, making it difficult to move around. This can lead to the loss of mobility and independence for the older adults. In the knee, this can in the knee, osteoarthritis can make difficult to walk, climb stairs, and perform other daily life activities. Till now, there is no cure for osteoarthritis except the joint replacement or surgery, but it can be prevented if detected early. This image shows the comparison between the normal knee and a knee affected by the osteoarthritis. Sorry. Let's take the closer look at the healthy joint on the left. As you can see, there is a smooth and intact cartilage covering the bones, which allow for the smooth, pain-free movement of the joint. Also, if we see the a joint affected by the osteoarthritis, here you can see that cartilage has worn away and exposing the bone underneath it. The joint space has also narrowed and bone spurs can be seen on the edge of the joint. These changes result in pain and stiffness and reduce mobility of the joint. Overall, this image serves as a visual representation of the degenerative changes that occur in the knee joint affected by the osteoarthritis. It highlights the importance of early diagnosis and treatment to prevent further joint damage and improve the quality of life for those affected by the condition. As discussed earlier, some signs and symptoms for the osteoarthritis are pain or itching, stiffness, decreased range of motion, and swelling. Now let's discuss the risk factor for the osteoarthritis. Osteoarthritis is a common form of arthritis and can affect anyone, but certain factors can increase your risk of developing osteoarthritis. Age or joint injury or overuse of the joint can certainly cause the osteoarthritis. Joint injuries or overuse can include injuries from sports or accidents, as well as the repetitive movement that puts stress on the joint. Not only this, being overweight can also increase your risk of developing osteoarthritis. The extra weight puts the more pressure on your joint, cause them to wear down faster. In addition to this, genetics can also osteoarthritis can transfer from generation to generation due to genetics. Also, in women gender, there are more chances of the osteoarthritis as compared to gender in male gender because of the hormonal changes that occur in the woman after the age of 50. Now let's have a look at the literature review. We have read the several papers. A few of them are stretchable, skin-mountable, and wearable strain sensor and their potential application. In this paper, we come to know the strain sensing performance of recently reported strain sensors are comparatively studied and discussed, showing that appropriate choice of the composite structure as well as suitable interaction between functional nanomaterials and polymers are essential for high-performance strain sensing. Second paper we read is the strain sensor based on the optical intensity change through the carbon nanotube embedded elastometer. In this paper, we come to know about the optical transmittance-based strain sensor is consisted by the light source, light detector, and functional film which transmittance changed by the external strain. Functional film is a carbon nanotube embedded elastometer and it changes its visible light transmittance by the strain. Another paper we have read is optical type strain sensor based on variable transmittance of carbon nanotube embedded elastometer thin film. In this paper, we come to know about the external tensile strain is applied to the CNT elastometer films. Cracks on the film are generated and propagated, leading to an increase of optical transmittance of the CNT elastometer film, which can be detected by the photodetector. Then there was highly stretchable sensitive strain sensor based on the silver nanowire elastometer nanocomposite. It reports highly flexible, stretchable, sensitive strain sensor based on the nanocomposite of silver nanowire works and PDMS elastometer in the form of sandwich structure. The paper we also read was about the biocompatible soft fluidic strain sensor and force sensor for the wearable device. In this paper, strain sensor based on the liquid conductor and the challenges faced by them are discussed. First of all, the linearity does not remain stable, which limits the application of conductive liquid sensor. Secondly, the used conductive liquid, which are not safe to implement it on or within the human body. Flexible sensor from the material to applications. In this academia work on we discuss the different method to increase the efficiency of the strain sensor to show the stretchability, linearity, stability. This report shows that the material and design procedures have significant effect on the performance of flexible strain sensor. Last but not least, the paper we have read about was about highly sensitive mechano-optical strain sensor based on 2D material for human quality gates monitoring and high-end robotics application. This research article presents highly sensitive mechano-optical strain sensor that is based on 2D material. The sensor is designed for the use of monitoring human quality gates as well as the high-end robotic application. Now, how our sensor differ from all these? In our sensor, we have used a novel design and novel material that is graphene. Also, our sensor is more sensitive with all the among all these mentioned sensors. Now let's discuss our aims and objective. Our aim was to design, model, and fabricate novel optical type flex sensor, to develop a working portable prototype for easy readover of the sensor data, and to develop a user-friendly mobile app for monitoring the activities. Moving towards the methodology of the strain sensor, we started with the mixing. Starting with the mixing of the two parts of the EcoFlex 0030, part A and part B in equal ratio, that is 1:1. We poured the mixed EcoFlex in the 3D mold designed by the 3D printer and designed by the SolidWorks and printed by the 3D printer. Also, we made the sensing layer by mixing the graphene in the EcoFlex and leave it to cure for the 4 hours. Left it. After that, we made the layer for the LDR and LED. When these layers are half cured, we place the LED and LDR on it. After that, we joined all three layers, that is sensing layer, LDR layer, and LED layer in such a way that sensing layer was in the middle, LDR and LED was facing the sensing layer. Here is the complete package here is the complete package or completed sensor. After that, we moved toward the mobile app development and showed the result on the Blink app. Hardware components we used are EcoFlex 030, ESP32 module, 3D printer, magnetic stirrer with bars, graphene, weight machine and beakers, SMD LEDs and LDRs. Software we used are SolidWorks, Eagle, Arduino IDE and Blink app. Here are the 3D molds we designed. Mold A to embed all three layers and mole B is for the LED layer and mole C is for the LDR layer. Here is the picture of EcoFlex part A and B and how we use the weight machine to mix them in the equal ratio. After that, we put the EcoFlex in the mold designed by the SolidWorks. We mix the graphene in the EcoFlex using the magnetic stirrer. After that, we place the LDR and LED on the half-cured EcoFlex layer. When the both LED and LDR layer are fully cured, we embed it with the graphene layer. And here are the final results. We designed the PCB for the 5 sensors for the wireless communication of 5 sensors. Here is the picture of our data transfer of our sensor. In this picture, we can see that the stretching, as we stretch the sensor, the graphene particles started to disperse. As a result, more light transmitted to the other end, that is at the LDR. Here is the sensor response. We can clearly see that initially our result is linear, and after that the response of sensor is moving toward more constant response. It is because at one time we completely stretch our sensor and no more graphene particles disperse from their place. Here is the response of 3 sensors. After that, we check the stability of our sensor. Here is the stability analysis of 60% strain, and here we can see that our sensor is highly stable, and we can only see a slight difference in the value over the time. Then this is testing at different stretching level. We test our strain at 0% strain, 40% strain, 80% strain, and 120% strain. And we clearly saw the stability at different strain level of our sensor. Loading and unloading of the sensor is highly symmetrical in opposite direction. We test the loading and unloading of the sensor at the 50% strain. Now let's move toward the work done in the medical application. The sensor was attached to the joint of human body and results were analyzed by moving the joint at different angles. We used blink cap for showing data of the sensor wirelessly. Initially, we mount the sensor on finger by fixing it to 2 ends. The results are analyzed by bending the finger from normal position to different angles. Here is the result shown at the blink app. While not only this, but this result is obtained on the blink app wirelessly. Now let's have a video demonstration and our whole FYP journey process. We start with the mixing of the EcoFlex. Here is our 3D printed mode, and we use the magnetic stirrer to mix the graphene with the EcoFlex. Here are the different sensing layers and EcoFlex layer we made. Now this video clearly shows the slight bending to have a great difference on the resistance of the LDR. You can clearly see the difference of the resistance on the slight bending. Sensor with blue LED. Are the results on the blank app. So to conclude, we have developed a novel type of strain sensor that utilizes stretchable polymer embedded with graphene as a conducting material on which the performance relies on the optical transmittance. When an external strain is applied, the optical transmittance increases, causing a high-intensity light to be detected by the light receiving device. Moreover, the sensor is capable of high stretchability of up to 150%. And demonstrates the stability through loading and unloading and stability tests. The sensor package, which includes light source, light receiving device, and polymer, can be mounted on human joint for the detecting of osteoarthritis. Moving toward the future recommendation, the next step of our project is to implement AI model to detect osteoarthritis. Also, there is a need of the central app which is used to display the data acquired from the sensor. In our work, we need to upload the code again and again in case of changing the Wi-Fi network. This act must be overcome by putting some advancement in this project. Furthermore, same result can also analyze in future by using different material instead of graphene, which was used in our case. Similarly, basic EcoFlex 030 can be replaced with any other substrate for the developing of thin film. Here are the references from where we gather data. Thank you so much. And don't forget to follow and subscribe to our channel.